Hello and welcome to another one of our online lectures here with the DiffEQ crew. And today we're going to take a look at section 6.4. We're going to talk about Dirac delta and impulse response. Let's go ahead and let's actually start by talking a bit about the unit step function, which, in most cases is regarded as one of the simplest piecewise continuous functions, but overall is a discontinuous function. And we define the unit step function in the following way. We call it u of t for that unit step function. And we say that it's 0 for t less than 0, and that it's 1 for t greater than or equal to 0. So if I wanted to get a visualization as to how this looks, draw my axes, and then get an idea. We'll do blue for the graph. We'd say up to at t equals 0, this will be my t-axis, the horizontal axis. The function is 0, but then at 0 and afterwards, it just steps up to 1. And use your imagination that those are horizontal looking lines. We have the t-axis and then call it the y-axis or the u of t-axis. So that's in general how our unit step function is going to look. And so it does nothing, and then at 0 it jumps up, and then it's up at 1, and it just continues on doing that. And we'd say because this unit step function can only take on values 0 or 1, the Laplace transform of it is actually pretty straightforward for this simple yet humble function. And the Laplace transform is only going to exist when the unit step function takes on the value 1, which is when t is non-negative, and we get the following result. So we actually looked at this before, early on in the chapter, but the idea is that the Laplace transform of the unit step function, we'd say whenever it takes on the value 0, it just gives us the definite integral of 0, which is 0. But when it takes on that value 1, which would be from t equals 0 to infinity, the unit step function takes on the value 1, we get 1 times e to the minus st. We're integrating with respect to t. And we would go through this. We actually did this one back in section 6.1, but this would give us the result out of 1 over s. And it's really just the same as taking the Laplace transform of 1. So this is a common result for us. So we can sort of keep that in mind, sort of unveil some of the mystery of the unit step function that way. But we can sort of clarify a bit further here that the unit step function doesn't have to take the jump at t equals 0. Rather, this jump discontinuity that we see could occur at some other value, some value t equals a. So we get sort of a more general idea as to our unit step function. And here we can go ahead and get a picture, do my axes again. And let's say, for example, that the value a is right here. Let's say, well, how is our unit step function going to look if there's a bit of a shift? We'd say everything leading up to a is going to take on the value 0. So we're at 0. And then right when we get to t equals a, wherever that is, we would then jump up to 1 and continue on. So it's the same idea, just we've now shifted a bit. And same idea here, I have my t-axis and my y-axis. Pretty cool stuff. All right, so let's go ahead and continue on. We want to know what is the Laplace transform of this unit step function with the shift using the formal definition. And notice here that the bounds are a little bit different. So if I want to go through and show this, I can. But keep in mind that we're not doing the jump from 0 to 1 at t equals 0. Instead, the jump from 0 to 1 happens at t equals a. So in fact, this lower bound is going to change. Now, it's still the same basic idea. We're saying, okay, whenever the unit step function takes on the value 0, there's nothing useful that we get from the result of the Laplace transform. But when it takes on the value 1, then we're going to get something out of it. So we'd say here I want to set this up, the definite integral of 1 times e to the minus st with respect to t. And my bounds should be not from 0 to infinity, but from a to infinity. Now this is an improper integral. We don't like improper integrals. We want to rewrite them as limits of proper integrals. So this is the limit as some dummy variable b goes to infinity. And then the integral from a to b of 1 times e to the minus st, or that's just e to the minus st dt. Still got to keep that limit notation. So I'd say limit as b goes to infinity. If I integrate e to the minus st with respect to t, I get e to the minus st divided by minus s. And that's from a to b. And then I would probably rewrite this a bit. I would say limit as b goes to infinity. I would bring this minus s in the denominator out in front. So write that as a negative 1 over s. And then times e to the minus st. Well, I would probably write this as 1 over e to the st. And since this has the t on it, this is where we're going to be plugging in the bounds, which are going from a to our dummy variable upper bound of b, which we'll evaluate in the limit later. Still got to write the limit notation. Limit as b goes to infinity. Yeah, you got it. Negative 1 over s. And now I can plug in the upper bound, the lower bound, subtracting between. We're plugging in for t. So this would be 1 over e to the s times b minus 1 over e to the s times a. And there's not really too much we can do with this aside from now talking about the limit as b goes to infinity. And remember, it matters sort of the condition that we place on s. But the idea is that here, if s is positive, then as b goes to infinity, this exponential function grows without bound. Since it's in a denominator, it's going to tend to 0, right? That denominator is going to get bigger and bigger, so the fraction gets smaller and smaller, tending to 0. So let's say, well, that goes to 0. And then taking this limit, we're going to get negative 1 over s times 0 minus 1 over e to the s times a, which here then we could multiply this out. Negative times a negative is positive. We'd say this is 1 over s times, and just as a standard convention, I would maybe write this as e to the as instead of e to the sa. Doesn't matter, no. And depending on where we're looking for this result, so this is, I think, looks great. We may see it, in a textbook or something, actually written with the exponential function on top. So another way we could write this, which might even be more common, is e to the negative as power all divided by s. They're the same results. So we notice that it's a bit different, right? If we have the unit step function that jumps at t equals 0, we just get the result 1 over s from its Laplace transform. If we take the unit step function in a more general sense and say, well, what if it doesn't jump at 0 but some other value a? Well, then in that case, we get this e to the minus as all divided by s from its Laplace transform. And this is more useful because even if a were to be 0, well, I could plug that in here and get the other result out of it. So this is a bit more multi-purposed, a bit more general for our use. Pretty nice. All right, some cool stuff to keep in mind. This result that we just showed, that e to the minus as divided by s. And then another sort of cool result here, if I were to take the Laplace transform of that unit step function, treating it generally, times some function of t minus a that's also been shifted, then, we could write it this way. This is a shorthand notation. If there's a shorthand notation, this use of a, we could also call it u of t minus a, but it's really just a shift. And this gives us the result e to the minus as times f of s. And we can think about it really connecting these two ideas. Only in this sort of upper example, we would say, well, the function f is just 1. So if the function f is 1, then we get this f of s is 1 over s. Something to sort of keep in mind. Hey, hope you're feeling great. Hope everything's going really well. Let's go ahead, let's keep talking. I like to talk about this stuff. Let's talk about the Dirac delta function now. Enough about these unit step functions. But these two have sort of a nice connection that we can think about. With the unit step function, we have a situation where, nothing is happening for a long time, and then bam, something happens, and then it continues, right? So that's sort of an interesting idea to think about, something to consider. If we're talking about an impulse, then what we're talking about is, nothing happening, and then bam, 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 bam. Something happens, and then back to nothingness, right? So it's sort of an interesting idea, sort of a nice contrast to the unit step function. If you want to think about how that would look, get my axes. We've been doing the baby blue. Let's do the baby blue. We got up, nothing happening. We're at 0, bam, and then back to nothing happening. This is kind of a poor drawing of it. I'm using my tablet, so not going to look so great. But in general, we'd say with an impulse, nothing happening, we get this sort of spike behavior and then back to nothing happening. Sort of an idea as to what the Dirac delta function would look like. And we define the delta function in the following way. We'd say, call it delta of t. It's going to be 0 when t is not equal to 0. But then when it's equal to 0, we get a spike that goes to infinity. So this unbounded spike in the positive vertical direction. That's what I'm trying to depict here. Now, we can't obviously draw the spike up to infinity, so some standard notations have us just drawing an arrow to sort of indicate that. Oops, it's not, you know what an arrow looks like. I can tell you're judging me right now. You know what? What am I going to do about it? Nothing. It's the internet. There's nothing I can do about it. And so this is the Dirac delta function. We have this sort of infinitely high spike at t equals 0. And very important, coinciding with this, we would say if we were to integrate this from negative infinity to infinity, our delta function, that the result would give us 1. And this is saying that the area of the delta function is supposed to be 1. This isn't something that we compute and discover. This is a definition that we give. We say our Dirac delta function is defined in this manner where the area of the function is 1. If you think about it too, since we're just having the spike happen at a singleton value just at t equals 0, that spike would have to be infinitely high because there's really no sort of width to consider. It's just at that singular value that we see the spike. Since there's no width, in order to get some area, some non-negligible area, in order for the area to be 1, we really need to sort of do something crazy with the height of it. And these are sort of some loose interpretations here. Obviously infinity isn't quite a number, it's an idea, it's a concept, something that keeps us up all night. But that's sort of the basic premise behind this. And very important to remember that we define the area of the delta function to be 1. But then similar to what we did with our unit step function, we can also generalize the delta function a bit further to start talking about non-specific values. So instead of the spike happening at t equals 0, the spike could happen at some other value t equals a. So for example, let's do a quick little drawing here. Got to get the yellow. The chalk, the yellow chalk. Let's say here's our axes. And we'd say, well, it doesn't have to happen, the whole show doesn't have to happen at 0. It could happen at some value a, where we got nothing going on, and there's my spike, and then back to nothing going on. So we could have a shift on that delta function. And we still define it here to have the area equal to 1. And here we would just give it a slight variation on the notation. We would do delta with a subscript a of t, just to sort of indicate that it's not the traditional one with the spike at 0, here we have a spike at a. And we can think about a lot of different phenomena where this Dirac delta function makes sense, where we would have sort of this spike or this impulse. I like to play guitar, you probably know that. So, you slam on one of those strings and, all of a sudden you get an impulse, right? And then, if you were muting it, then you would get that fast decay that you would see with an impulse. And you could probably think of some other examples. Let me know, in the comments. Let me know over on the discussion board for the course. Let me know what you think would be a good example of one of these delta functions with these impulses. Or if you have a good idea as to what you think would be something similar to a step function, let me know. Let me know. Let's talk about it. It's kind of fun to think about. Let's talk about this a bit further. So let's say that our impulse occurs between two values, and not necessarily at a singular value, but over some range of values from negative a to a in the t direction. Then we really want to be focusing on and preserving the idea that the area is 1. So in this case, we would need the height of the impulse to be a bit more restricted. It wouldn't just go to infinity then. We would say in particular, if I'm between negative a and a with that nice symmetry, I would need the height of the impulse to actually be 1 over 2a. We would define it in the following way, and here I've just changed my notation to a d sub a of t. Since it's no longer a spike happening at a singleton value, I have a range. And we'd say that the delta function takes on the value 1 over 2a on the range of values from negative a to a, but then a 0 elsewhere. And if I want to get a cool picture of this, I certainly can. Try to make this look kind of reasonably symmetric. Negative a to a. How would my delta function look? Well, we'd say here we got nothing going on, 0. And then at negative a, we're going to be up at 1 over 2a, so that would be the height. And we're just going to sort of coast there until we get to a, where we're back down to 0 now. And that's how this would look, right? And we'd say in particular, this height that we have would be 1 over 2a. Now we can see that the area is 1. In fact, there's a lot of ways we could justify this. If I look at this and view it as a rectangular region, I could say, well, if I'm thinking about sort of width times height, well, here the width would be from a to minus a, or that would be a minus minus a, times the height is 1 over 2a, which would give me a minus negative a is a plus a, which gives me 2a, times 1 over 2a, which gives me 1 if I'm just treating it geometrically. We can also think about this using some calculus. I'm just going to sort of, whoa, where am I going? You can never catch me. We drew it in sort of a calculus manner and say, well, what if I wanted to integrate the function over this region where it's non-zero from negative a to a, and my function is this constant valued function where the output is 1 over 2a, and we would integrate this with respect to t. We would say, well, integrating the constant function just brings the variable back into play. So that gives me 1 over 2a times t from negative a to a. And then from there, it's really the same computation. We would say, okay, 1 over 2a can hang out in front as a coefficient. When I evaluate the net change in t from negative a to a, I get that a minus negative a, or that this is 1 over 2a times a plus a is 2a, gives me 1. So we can talk about this in terms of calculus, we can talk about it geometrically, but we see that we have to sort of adjust the height of the impulse in order to maintain or preserve that the area is 1. Really kind of cool stuff. Now, a good question to ask is what happens as a gets smaller and closer to 0? And we can think about this visually. But then I also want to sort of think about it in terms of a limit as well. So if a gets sort of smaller and closer to 0, let's say a, negative a, and a are here, you'd say, well, what would have to happen to compensate? Well, to make sure that the area is still 1, since we don't have so much width to the rectangular region anymore, we would need to get a bit more height out of it. Oh, and this is, please don't let anybody know in the real world that I drew a rectangle that looks like this. I don't feel good about it. That's a perfect line too. We see we get a little bit more out of the height in this case. But we can think about it in terms of a limit as well. We'd say, well, if I have to take a look at, so I guess maybe the question isn't what happens as a, well, what happens to 1 over 2a as a gets smaller and closer to 0? We'd say 1 over 2a, if I want the limit of this as a goes to 0, what would this give me? Well, it's going to go to infinity, right? So we'd be able to say that as a goes to 0, 1 over 2a goes to infinity. And we could sort of continue this on and on and on. We would say, well, if I want to get even closer to that sort of vertical axis, well, to compensate for that, I would need this much higher impulse. And if I were to actually keep going, doubling in on each side to get to 0, I'd get that spike that we were taking a look at earlier. I would get that classic spike at 0, heading to infinity. So notice that our area is still 1, but then the vertical spike would head to positive infinity. On top of this, we can also consider shifts and scaling on the delta function as well. These would just behave normally, right? What we would expect. We have some important results here to sort of consider, some things we've talked about. The Laplace transform of the delta function would give us 1. Laplace transform of the shifted delta function t minus a is the shift, would give us e to the minus as. And then this is a result that we had previously, but now I have it written in terms of the inverse, which is going to be helpful for what we're doing. We have the Laplace inverse of e to the minus as times f of s is going to map us to the function of t. It's going to be u of t minus a times f of t minus a. So that would be the unit step function with a shift by a, and then a function of t with a shift by a as well. And let's go ahead and take a look at solving the following differential equation using Laplace transforms. Let me actually use some of this extra space up here. So I have x double prime plus 4x equals delta of t. And we have initial values x at 0 is 0 and x prime at 0 is 0. So let me go ahead and take Laplace transform of both sides. So Laplace transform of x double prime plus 4x equals the Laplace transform of delta of t. And I can use linearity of the transformation to break this up. So this is the Laplace transform of x double prime, and then plus, and I can bring the 4 out as a coefficient on the transformation. So 4 times Laplace transformation of x equals the Laplace transformation applied on delta of t. And now we can think about this in terms of an initial value problem like we've been doing before. So Laplace transformation on x double prime is going to give me s squared times capital X of s minus s times x at 0 minus x prime at 0 plus 4 times the Laplace transformation on x just gives us capital X of s, or you can use f, whatever you prefer for your notation, equals, and then Laplace transformation of delta of t, well, we have that over here, that's just 1 by definition. And now what's nice about this is we said x at 0 and x prime at 0 is 0. Since x at 0 is 0 and x prime at 0 is 0, those terms drop out. So I'm left with s squared times big X of s plus 4 times big X of s equals 1. And then I can solve for this capital X of s. So we'd say factor it out times s squared plus 4, and then equals 1. And then we can divide. So capital X of s is equal to 1 over s squared plus 4. Now, of course, we want to solve the differential equation, so now we have to get the corresponding function of t is what we're going to need. So we'd say, well, this kind of looks familiar. What can I do to modify this? Well, good question. I would say think of this like 1 over s squared plus, instead of 4, think of that as 2 squared. And really what I want is I want a 2 on top. So I can relate this back to a common form. So I can put a 2 on top so long as I'm willing to divide by a 2. Let's get back to our yellow. And I can now think of this as, I have this 1/2 that's just sort of a byproduct of the, manipulation that I've done. But now I have my 2 over s squared plus 2 squared. And let me know if you know what this is going to map back to in terms of a function of t. Yell it at your computer screen. Let me know. Let me know, because I'm about to let you know. If I do the Laplace inverse on this 1/2 times 2 over s squared plus 2 squared, or s squared plus 4, whatever. 1/2 is going to come along. We'd say this 2 over s squared plus 2 squared is going to give us sine of 2t. And that this would be our function. You want to call it little x of t or little f of t, whatever you want to call it. This is our solution. So here we get a 1/2 sine of 2t. And we get a chance to work with our delta function in this case. So, hey, pretty cool. Let me know what you think about that. We'll take a look at a couple more examples. So here I want to solve the following using Laplace Transformation. So we can go ahead and take the Laplace Transformation of each side. We have x double prime plus 4x prime plus 4x equals 1 plus delta of t minus 2 with initial values x at 0 is 0, x prime at 0 is 0. And let me go ahead and apply the Laplace Transform, and let me go through the linearity as well. So let's say the Laplace Transform of x double prime plus 4 times Laplace Transform of x prime plus 4 times Laplace Transform of x equals, and same idea on the other side as well. I'm going to take the Laplace Transform of it, and then I'm going to split it up with linearity. So Laplace Transform of 1 plus the Laplace Transform of delta of t minus 2. And I can start using the identity. So here Laplace Transform of x double prime gives me s squared times capital X of s minus s times x of 0 minus x prime at 0 plus 4 times Laplace Transform of x prime, that's s times capital X of s minus x of 0 plus 4 times Laplace Transform of x gives me capital X of s equals, and I'm at the other side, running out of room, but let's see if we can get it. Laplace Transform of 1, we saw that earlier, is 1 over s, plus the Laplace Transform of the delta function of t minus 2. So what do we say about that? Well, Laplace Transform the delta function of t minus a is e to the minus as. So the Laplace Transform of the delta function of t minus 2 is going to give me e to the minus 2s. And there we go. Now, cool to remember that x at 0 is 0 and x prime at 0 is 0. So that's going to drop out. That's going to go. This is gone. And should have enough room to safely write what's left. I have s squared times capital X of s plus 4s times capital X of s plus 4 times capital X of s equals 1 over s plus e to the minus 2s. And I want to solve for capital X of s, so I'd factor it out. And that leaves me with s squared plus 4s plus 4 equals 1 over s plus e to the minus 2s. And then I would want to divide both sides by this. Now, I'm not going to divide everything in maybe a traditional sense. I'm going to divide everything, of course. I have to. But I'm going to sort of treat them separately. So I'll say capital X of s is equal to, I'm going to divide this one here. So I'll say that's 1 over, it's going to be s times s squared plus 4s plus 4 plus, and then this other exponential term here, e to the minus 2s, needs to be divided as well by the s squared plus 4s plus 4. So okay, so we've done it. So this is, I think, a little bit better, a little bit easier to work with and manipulate than just dividing everything kind of blindly. So here we sort of do it strategically to each of the terms. And this one's going to be some more work still, right? These aren't always going to be fast or straightforward, so let's get working. I can factor a bit more. So say capital X of S. Here I have 1 over, I can say S, and then this is S plus 2 squared, right? S plus 2 times S plus 2. Plus, and here I have e to the minus 2s divided by, and this is just that S plus 2 squared. Now we're going to work with these separately. We're going to have to do something very special with the second fraction. We'll be able to talk a bit about it. But for this first one, partial fraction decomposition. So we got a bit of PFD we're going to have to work with here. So here we can sort of think about this. So let's get a different color. I'm going to do something to try to work with this. So here I have 1 over S times S plus 2 squared. I can do a partial fraction decomposition, a case 1 with 3 of these, well, a case 1 and a case 2, that's what I have. I'm going to have A over S plus B over S plus 2, but then building to that multiplicity, I'm going to need C over S plus 2 squared, and that's the case 2 partial fraction decomposition coming in. But now I want to build back to that common denominator. So what am I missing for this denominator, A over S? I'm missing that S plus 2 squared, or we said S plus 2 squared was really S squared plus 4S plus 4. So I've got to multiply this by S squared plus 4S plus 4 over S squared plus 4S plus 4. B over S plus 2, that's missing an S and an S plus 2. And C over S plus 2 squared, that's just missing the S. And now I have that common denominator. Since the denominators are equal, and think about combining the like fractions, we can just focus exclusively on the numerator. Say 1 should be equal to A times S squared plus 4S plus 4 plus B times, and then what is this? It's S squared plus 2S. If I distribute, plus C times S. And if I expand this out, I got some good room here. We'll say 1 is equal to AS squared plus 4AS plus 4A plus BS squared plus 2BS plus CS. And I want to set like terms equal on the left and right. Now on the left, I have no S squared term, so we'll say 0 S squared should be equal to the A S squared plus B S squared. Where the coefficient on S squared on both sides, 0 should be equal to A plus B. Now we move on to the S terms. On the left, I have no S terms, so it's a 0S. On the right, what are my coefficients on S? I have a 4A from the 4AS. I have a 2B from the 2BS. And I have a C from the CS. So the 0S on the left is equal to the 4A plus 2B plus C on the S terms on the right. And what about just constants, or S to the 0? We would say, well, I have a 1 on the left, and the only thing that doesn't have an S or an S squared would be the 4A term. And this gives me a system of equations that I can work with. We would say here I have 3 equations, 3 unknowns. And it solves not too slowly. We would say 1 equals 4A. I can solve that right away and say that A is 1/4. We notice that 0 is equal to A plus B. So what does that mean? Well, that means that B is equal to negative A. So then B is a negative 1/4. And working with that middle equation, we should be able to solve for C. Well, if I solve for C, I would say C is equal to negative 4A minus 2B, moving those other terms to the other side. But I know what their values are. So negative 4 times A is negative 4 times 1/4, and then minus 2 times B is minus 2 times negative 1/4. Negative 4 times 1/4 is negative 1. Minus a negative is plus. 2 times 1/4 is 1/2. So C is a negative 1 plus 1/2, or that C is negative 1/2. So not too terrible. You know, we're doing work. We're working for it, but we got it. And now I want to go and write out that partial fraction decomposition. Now I'm just focusing on this left-hand side. And I want to go back to the fractions in purple that I had, and that was a over s, or let me write that as a times 1 over s, plus b times, that was 1 over s plus 2, plus c times 1 over, and then s plus 2 squared. So here I've just written this same partial fraction decomposition out generally, but I just like to pick the a, the b, and the c out, because if these are fractions, then it's not going to look nice if I just write it in the numerator. But I do know what they are, so let's go ahead and pop those values in. Let's do the purple. We did purple. A is 1/4. So we have 1/4 times 1 over s. B is negative 1/4 times 1 over s plus 2. And then C is, it's a plus sign there, but don't judge me, negative 1/2 times 1 over s plus 2 squared. And this is, fair to say the majority of what we have to work with for the Laplace inverse. There is still that other term that we have to work with. So let me jot that one back down. That was e to the minus 2s. I'll do that in yellow. E to the minus 2s over the s plus 2 squared. Now the first couple of these in the purple are actually going to be, I'd say, relatively common ones. Right? If we're thinking about using some inverse to map back, we'd say, okay, 1 over 4 comes along. 1 over s, the Laplace inverse of that is 1. And then minus 1/4. Do you remember this one? The 1 over s plus 2 might be helpful to think about it as s minus negative 2. That's going to give us our exponential term. In general, 1 over s minus a gives us e to the at. So this is going to give us e to the minus 2t. And then here I have my coefficient, minus 1/2. For this 1 over s plus 2 quantity squared term, we're actually going to have to think about something from a previous section where we talked a bit about translations. So we would say if I had the function of t given by e to the at, t to the power of n, and the corresponding function capital F of s would be n factorial divided by s minus a to the power of n plus 1. And it might be tricky to sort of see right away, so we get some practice with these. What I'm looking at here, I have a 1 factorial, and then I have stuff to the power of 1 plus 1, so that means n is 1. And what would a be? Well, it would be negative 2. So if I can sort of see that and make the connection, say, okay, 1 factorial, we have the power of 1 plus 1, which is 2, so n is 1. So I get t to the first. And then e to the at, well, a would be minus 2. So e to the minus 2t, and then times t. So most of this is done, right? I just have this remaining term here, this e to the minus 2s divided by s plus 2 squared. And this one's going to be kind of a bit tricky. So I have a good answer working here, but let me leave some space. Let's do the red. Let me work with this a bit underneath. So that was our e to the minus 2s divided by s plus 2 squared. And we're going to want to try to break this up. We're going to want to try to break this up into e to the minus 2s times 1 over s plus 2 squared. And we're going to work with a result that we mentioned earlier, but haven't really looked at yet, is this one here. The Laplace inverse of e to the minus as times big F of s is equal to u of t minus a times f of t minus a. So let me actually write that back down here where it's kind of relevant. We'll say Laplace inverse of e to the minus as times big F of s is equal to u of t minus a times our function little f at t minus a. Now, if I look at what's going on here, I can see my e to the minus as. It's this e to the minus 2s, and I want to use the Laplace inverse on this. But here, that means my big f of s is this 1 over s plus 2 squared. And we said earlier, well, that's kind of familiar to us. That's kind of that form that we saw where we would say 1 factorial over s minus negative 2 to the power of 1 plus 1. And that this would map to, it would be e to the minus 2t times t. We just got done saying that. So I want to keep that in mind. This is actually my little f at t, if I want to sort of think of it that way. So I'd say, okay, so but what I want is I want f of t minus a. And what is a in this case? Well, a in this case is 2. So I'd say, well, I can actually just follow this now to try to figure out what this should be. It should be the unit function at t minus a. That's t minus a is minus 2. And then it should be that function little f that I just found, but it shouldn't be of t. It should be a function of t minus a. So I'm going to use this as my framework, but everywhere I see a t, I'm going to have to replace it with t minus a. So that's e to the negative 2 times parentheses t minus a. And then instead of times t, it's got to be times t minus a. Sorry, t minus, whoops. Oh boy, we said a is 2. We said a is 2. So don't write it generally like I did. Don't be a fool like your father. Write it, we have negative 2, and then it's going to be t minus 2. T minus 2. A is 2. So here we have it. Our u of t minus a, that's u of t minus 2. Our function little f is this e to the minus 2t times t. If I want it as a function of t minus a, that means I want it as a function of t minus 2. So it's e to the negative 2 times t minus 2 in parentheses times t minus 2. So a little trick, sort of like solving the Da Vinci Code, but we can do it. And then we just want to go ahead and add this. Do I have room? Let me just jot it down at the bottom. So I already have these lovely parts that weren't quite as terrible. 1/4 times 1. This was the Laplace inverse. 1/4 times 1, which is 1/4. Minus 1/4 times e to the minus 2t. Minus 1/2 e to the minus 2t times t. So all of those pieces. And then with our new stuff, so we'd say plus. The last term was a bit sort of like a little puzzle for us, but we got it. That's u of t minus 2 e to the power of negative 2 times quantity t minus 2 times t minus 2. Pretty cool. Hope you like it. Well, all right, so what's next? We'll take a look at one last example for this section, talking about using Laplace transforms, working with our delta functions as well. So we'll take a look at one more of these. So we'll take a look at one more of these. We have x double prime plus 2x prime plus 2x equals 2 times delta function at t minus pi. We have x at 0 is 0, x prime at 0 is 0. Okay, so we start by taking the Laplace transform of each side. And I'm going to use linearity. So Laplace transform of x double prime plus 2 times Laplace transform of x prime plus 2 times Laplace transform of x equals, and I can take the Laplace transform of the other side. I can bring my coefficient out. So 2 times Laplace transform the delta function at t minus pi. We have an initial value problem. So we'd say Laplace transform of x double prime gives us s squared times capital X of s minus s times x at 0 minus x prime at 0 plus 2 times Laplace transform of x prime gives us s times capital X of s minus x at 0 plus 2 times Laplace transform on x gives us 2 times capital X of s equals 2 times, and then the Laplace transform applied on the delta function at t minus pi. So delta of t minus pi should give us e to the minus pi s. I can never make my way back. E to the minus pi s. And like we were saying, lucky for us, x at 0 is 0, x prime at 0 is 0. So x at 0 is 0, so that's gone. X prime at 0 is 0, that's gone. This is gone. So we're left with some stuff, but not everything. So let's clean this up. We have s squared times capital X of s plus 2 times s times capital X of s plus 2 times capital X of s equals 2 times e to the minus pi s power. And I want to solve for capital X of s, so I can factor it out on the left. I'm left with s squared plus 2s plus 2 in its wake, and equals 2e to the minus pi s. And then I can divide. So capital X of s is equal to 2e to the minus pi s divided by s squared plus 2s plus 2. And now I want to work with some Laplace inverse to try to map back to my function of t that would generate this function of s. And we'd say, well, it doesn't look like the denominator is going to factor. And I kind of want the denominator to be factored if I'm going to make any headway here. So what we want to do is we want to complete the square. So we have s squared plus 2s plus, and I'm going to leave some space, plus 2. Well, what do we do to complete the square? We have to make sure that there's no leading coefficient other than 1, since I just have one s squared, that's already done. But then I would want to go to the coefficient on s, which is 2, take that coefficient, and I cut it in half. Always cut it in half. We're going to share. So if it happened to be a 2, and if I divide it by 2, it's going to give me 1. So whatever that, if it was a 4, I would divide it by 2. If it was a 7, I would divide it by 2. If it happens to be a 2, I divide it by 2. I get this number. Whatever that number is, then I square it. In this case, it's a 1. I square it, it gives me 1. And this is my magic number. That's going to help me complete the square. So I go here, right after the s term, the 2s term, I want to add that magic number in. But I've changed it. This is no longer the same as what it was. So in order to balance, I have to subtract 1 out the other side. So well, it's still the same. I've just added 1 and subtracted 1. So I haven't really changed it. I've done nothing illegal. Don't even try to bug me about it. But what's nice about this is I can now factor these first 3 terms. And say, well, here if I think about factoring this, I'm going to be able to write this as something squared. And for these last 2 constants, I would just combine them. We'd say 2 minus 1 gives me 1. But if I go back here, we would say, well, s squared plus 2s plus 1, that's going to factor to give me s plus 1 quantity squared, or s plus 1 times s plus 1. And this is the same. If I were to expand this out, it would, simplify to the s squared plus 2s plus 2, but it's in a nicer form for me to work with, to manipulate. So what do I have? Well, I have the 2e to the negative pi s, and then divided by, instead of the s squared plus 2s plus 2, I've completed the square, and we have s plus 1 squared plus 1. And I want to work with this. Well, now to work with this, I think it's actually helpful to break it up a bit. So I'd say, well, let me bring this 2 out, and let me bring the exponential term e to the minus pi s out, and say times 1 over s plus 1 squared plus 1. Now, in order to work with this, we're going to need another one of those translation definitions. So I'll go ahead and I'll write this over to the side. If I had the function f of t, which is e to the at sine kt, if you remember this one, then the corresponding function, capital F of s, would be k divided by s minus a squared plus k squared. And this is what we want to work with here. So we'd say, okay, looks pretty similar, in fact. We might just do a little bit of sort of manipulating. So I got 2 e to the minus pi s times, here I could say 1 over, instead of s plus 1, I could say s minus negative 1 squared, plus 1, or I could think of 1 as 1 squared. Now, in addition to this translation property, we're going to have to also think about, I'll do purple, what we said earlier. I'll go all the way back to where we had it. I think we wrote it down since then. It's Laplace inverse of e to the minus as times big F of s is u of t minus a times function little f of t minus a. Going to need that as well, of course, right? So we'd say in this case, let me write it down here so I have it, Laplace inverse of e to the minus as times capital F of s is going to give us u of t minus a times function little f of t minus a. We used this last time too. So what is important to do here is to actually be able to look at, I can see the e to the minus as term already. I have the 2, it's a coefficient, big deal. But I want to focus on this capital F of s, this 1 over s minus negative 1 squared plus 1 squared. And so we'll look at this. We got 1 squared, so k is 1. So k is 1. And s minus a squared, a is negative 1. So if I wanted to map this back to my function little f of t, we would say little f of t is e to the at, or that's e to the, where'd my minus go? E to the minus t, and then sine of kt is sine of 1t, or sine of t. Once I'm able to identify what that function little f of t is, I have to keep in mind that I should be shifting it. And it might seem like these never end, but we're actually pretty close to cracking the Da Vinci Code right now. So I'd say, okay, I know what little f of t is. I wanted the Laplace inverse of all of this. Darn right I do. So let's do it now. Laplace inverse. Now, important to look at this and to be able to discern, and this is sort of poor notation here on my part using sort of the a here and the a here, because I really want to keep in mind that when I'm talking about this function capital F of s and this function little f of t, I'm already done with that discussion. So I'm looking at the exponential function e to the minus as. And I want to look at this and say, okay, well, what is that a referencing? And you could change this. It doesn't have to be an a here. It might be smarter to change it so there's not any confusion. Let me know on the discussion board if I'm losing you here, but try to stay with me. Once I designate what little f of t is, if you're already using, a's and k's or whatever you got, just kind of forget about it. Wipe the slate clean, fresh start. I want to think of this as e to the minus as times capital F of s. Here's my e to the minus as. So we would say, well, what is a? A is pi. A is pi. Getting the building blocks right now. So okay then, so what do I want? I want my unit step function of t minus a, so that's t minus pi, times my function little f, not of t, but of t minus a, and again thinking about a as pi. So instead of e to the minus t, it's e to the minus parentheses, should be t minus, every once in a while I get a little bit of that stylus bleed, but it's worth fixing it because you're worth it. So I'm replacing t with t minus pi, and it's got a negative coefficient, so I want to preserve that. And then instead of sine of t, well, what should it be? It should be sine of, what do you think? T minus pi. And I think I'm almost done. I think I just forgot my coefficient, which was a 2. So there we go. Let's say, well, we've unmasked all of this. Just sort of recap, I used this definition, which also uses the character a, which was kind of unfortunate. That's a bit of a, I'm going to regret this later on. I'm not going to sleep at all tonight. I'm going to be, up all night upset about this. But all I did was I looked at this to try to match to this piece here to try to find out what little f of t is. Once I have it, forget about it. I know what it is. I know how I'm going to manipulate it. And I go to this form here, this e to the, and this happens to also be an a, e to the minus as. A's and k's and s's are very popular. I look at this e to the minus as times big F of s, and I say, well, okay, so here I'm really referring to a is pi. And I want to use that to build this final form. So we wound up with, let's get this nice, 2 u of t minus pi times e to the power of negative quantity t minus pi times sine of, I'm in the way, t minus pi. And that would be our function. You want to call it little x of t, you want to call it little f, whatever your notation is. That would be our solution to this differential equation working with this impulse function. So these are very interesting solutions, right? Maybe you're noticing, or maybe you're just noticing now, when I solve a differential equation involving this delta function, the solution is kind of interesting. The solution involves this unit step function with a shift along with these other pieces as well. So very interesting solutions, very interesting differential equations to solve. But hey, let me know on the discussion board what you think about these delta functions, the unit step functions, what you think about all of this information. Get the practice in, it does get easier. It's kind of fun to make these discoveries and connections. Very rewarding when we can work through these successfully as well. But anyways, thank you so much for your time. This is it. This is it for our course. Put the homework in the homework jar. 6.4. Dirac delta functions and impulse. Take a look at the homework. Get some practice in. Let me know. Keep me updated how you're doing. Let me know how you're doing on the material. Let me know how you're doing in general. Are you having a good day? Hey, yeah, this isn't the end of it for me. It's not the end of it for you either. So you know where to find me if you need me. But I hope you enjoyed this lecture. And you know what? No matter what you're doing, where you are, I want you to remember to keep learning, to keep dreaming, to always follow your heart. And hey, I'm going to see you next time. Take care of yourself. All right. Diffie Q Crew out.